There are one-of-a-kind friendship bracelets for all genders. They are made by people in Nicaragua. People will be selling them in the net during lunch and at all home basketball games before Christmas. Bracelets are $5 and purses are $10. The JV girls beat Bullock Creek with a score of 56-11. Delaney Cote led the G's with 11, followed by Katie Briel and Sydney Conley with 8 each. Sarah Mason, Ashley Payne, and Heidi Indigo had 6. The 18th annual Magical Dinner is Friday, December 8th, and Saturday, December 9th at 6 p.m. at 11 French Street. The cost is $20 for adults, $15 for alumni, students, seniors, veterans, and staff, and $10 for children 10 and under. This year we are featuring a brand new buffet from Max on Main. The buffet includes warm sale, fresh vegetables, chicken skewers, lemon and teriyaki, barbecue, and classic, roasted red skin potatoes, corn on the cob, coleslaw, macaroni salad, baked beans, potato soup, broccoli soup, bread for dipping, and brownies. This year's show features Wings of Harmony, Bella Voice, and Forte Men's Ensemble. This show is hilarious tales of the Ring of Lies. There are also some fun 5-minute Shakespeare skits. Tickets are on sale at Gladwin High School. Choir members, Wild Flowers, and Max on Main. Don't miss this beautiful and fun Christmas tradition. And for your joke of the day today, why was Santa's little Why was Santa's little helper depressed? He had low self-esteem. Everybody have a great day.
All right, guys. If you were gone yesterday, then you're like, what the heck is going on with the warm-up right now? Because we didn't hear the announcement yesterday. So I've handed out an exam study guide packet with all your exam study guide questions. Is there anyone that still needs that because you were gone? Okay, so don't write the answers on your packet. We're going to write all the answers on notebook paper. We did 1 through 4 yesterday, so if you were gone, you can copy those from a friend or figure them out for yourself, but you do need to do them. And then today we'll put 5 through 8 right underneath the ones that we did yesterday and just keep going. After we're done with our exam study guide questions, then we'll get back into our notes for a little bit. We just started a new chapter. Partway through the notes, I'm going to stop and do a checkup to see if you're getting it. And then we'll do a little bit more notes. And then near the end of the hour, I'm going to hand out your homework. If you passed the checkup, you can get going right on your homework right away. And if you didn't pass the checkup, then you'll work with either Andrew or myself so that we can help you understand what we're doing. So that's the plan for today. Your homework will be due tomorrow. But once you get it, the homework goes fast. So here we go. Number 5 from the exam study guide says, what are controlled variables? Yesterday we said the independent variable is the one thing you change on purpose because you want to see what it'll do, and the dependent variable is the thing that you measure or observe at the end to see if it did change like you thought it would. So then what are the controlled variables? Eric? Yep, all the stuff that stays the same because you don't want it to interfere with your results. You don't have to write as much as I did, guys. You can shorten it up, paraphrase, do sentence fragments instead of full sentences. Write down what you think will be useful to you while you're studying for the exam. Number 6, what is the difference between the control group and the experimental group in an experiment? Or last year in biology, if you did the greenhouse experiment, you had a control plant and an experimental plant. Which plant is the one that you did something strange to, that you put your independent variable on? Zach?
The experimental.
The experimental, good. And so then what's the control?
The one you're not working on.
The one you're not working on, the one you just kind of leave the same, so you know what normal is. You need to have a control group to compare your experimental group to. So the control group does not receive the independent variable, and the experimental group does. And then you'll kind of know like what your group or your plant or your trial would have done without the independent variable, so that you know whether the independent variable made a difference or not. Right, number 7, let's say you finished an experiment, you typed up your report, now you're going to submit it for peer review. What's going to happen when your report is peer reviewed? Who looks at it? Your peers. What are your peers? Not just your friends, like typically like your peers, Caleb Kish's peers right now are like your friends and the other students because they're similar to you. But now, in our scenario here, like you are an adult, you are a scientist, and you've done research. Who are your peers if you're an adult scientist doing research? Other adult scientists doing research, right? In a similar field or the same field. So when you submit it for peer review, your peer is another scientist who also has expertise in this area. All right, so now it's in the other scientist's hands. What's that scientist going to look for when they're reviewing it? What'd you say? Flaws. Good job, Shelby. Do you want to add? Repeatability. They're going to look at, for flaws, it might have just been something that happened on accident during the experiment, or the flaw might have been the way the experiment was designed to begin with. So they're going to look to make sure there's a valid experimental design with only one change, so you know that that change caused the results. Remember the ice cream sales juvenile arrest thing? What were we talking about with that example? Yeah, there is a correlation. When ice cream sales go up, juvenile arrests go up. There is a correlation. But correlation does not always mean causation, that one caused the other. So they will look for other possible interpretations of the data. Just because the data is legit, does that really mean what you think it means, or is there another explanation? So those are some of the things that they'll be looking for. So other scientists will look for other possible interpretations of the data, accuracy, honesty, potential sources of error, reproducibility, and so on. They want to make sure that this is good stuff before it gets published. one for today. Describe the shape of a line graph that relates two variables that are directly proportional and then also inversely proportional. My smartboard won't let me write on it today for some reason. So here's your graph. For directly proportional, should I slant up or down? Up. Yep, you want a positive slope for directly proportional. And so then inversely proportional must look like what? Yep, it slants down with a negative slope. So you can either sketch like I did on the chalkboard, or you can write it out like this. If they're directly proportional, the graph will have a positive slope, and if they're inversely proportional, the graph will have a negative slope. You can either write or sketch, whichever you like better. Take your time, but when you're done with the exam study guide questions, please get out your notes, the chapter 6A notes that we just started. I don't really want you to miss what we're doing today. So can you do it during IT?
Yeah, I forgot this.
And Michael, hey, you were the other one. I know you have seats ready, but when you get back and there's like 10 minutes left, can you come and try to finish up your test?
Yeah.
Okay, do you need one of these so they'll let you come down the hallway? Just a pass? Okay. You can't get over it. Alright, is anyone still using the warm-up?
She made me go grade papers, so I didn't really know what to do, so I just kept reading. It's like I had stuff here. They completely forgot about me. So I have to do a lot.
If it was real, you would just like hide.
I would have probably done that. They're all crazy at the point.
Alright, is anyone still using this now? In this place? So. Okay. Yesterday we were talking about valence electrons and how to represent them with electron dot diagrams. So remember, an atom has a nucleus and then several different energy levels, but the valence electrons are the ones in the outside level. Those are the only electrons we really care about. If you want to know how many valence electrons something has, look at the tall column. And at the top of the column, there will be a column number. And if it's in columns 1 or 2, column 1 has 1, column 2 has 2. And then when you get to the other tall columns on the right, 13 through 18, you subtract 10. So 13 has 3, 14 has 4, and so on. Now you represent those valence electrons by dots, and you do an electron dot diagram. So beryllium, for instance, is in column 2. It has 2 valence electrons. So all you do is write Be for beryllium, and then put 2 dots by it. The only thing that I'm going to be picky about is where you put your dots. There are 4 sides to the VE symbol. There's a top, a bottom, left, and right. There's 4 places you can put dots. If you have 4 or less, I want you to spread them out so that they are not doubled up. The only time you're going to start doubling them up is if you have more than 4. So by the time we get to nitrogen, which is in column 15, it has 5 valence electrons. So you would spread out first when you do your first 4 dots, and then when you get to number 5 and you have to double up, you double up once. It doesn't matter which order you go in. It doesn't matter if you double up on the side or the top, but it does matter that you spread them out first and only double up if you have to. So there are like 20 different examples of electron dot diagrams up here on the board right now. Please choose 2 or 3 of these and put them in your notes right there where it says, here are some examples. Try to choose like one from the left with just a few dots and one from the right with more, and put those in your notes, please. Today, when we get partway through the notes, I'm going to give you a checkup. Some things that are going to be on your checkup are, I'll just give you an element and then I'll ask you questions about it. And I'll ask, how many valence electrons does it have? And I'll ask you to draw the dot diagram. I will also ask you how many total electrons it has. Valence electrons are in the outer shell, but if you also counted the electrons on the inner shells, which are not shown in the dot diagram, how many would it have? So do you guys remember that from a previous unit? Chlorine, for instance, Cl. How many total electrons does it have? How many protons does chlorine have?
17.
17, because its atomic number, the blue number that's right in the box with it, is 17. So if you have 17 positive protons, how many negative electrons do you have since you're a neutral atom right now?
17.
17. So chlorine, since its atomic number is 17, that blue number right in the box, means that it has 17 electrons total. It goes 2 in the first shell, 8 in the second, so that's 10 so far, and then 7 in the third to make it 17. When we draw the dot diagram, we only draw the 7 dots because we're drawing the electrons in that third shell or the outer shell. But remember, there are electrons on the inside shells too. Those shells are just all filled up. So when you draw like the Cl symbol, the Cl represents the nucleus with all the protons and neutrons, and it represents those inside energy levels that are full. Like the nucleus and the inside energy levels are not drawn because we just do Cl instead. And then the only part you draw are those dots that are in the outer shell. All right. So you guys already know, I believe, that every element wants to have 8 valence electrons, or a full outer shell, and that gives it a stable electron configuration. Everybody wants to be like the noble gases, full outer shell, stable and happy. It's called the octet rule. Of course, the one exception to that rule is helium. Helium is in column 18. So you want to go, okay, well, column 18 minus 10 is 8. Helium has 8 valence electrons, right? Well, wrong, because helium's blue number, the atomic number, is 2, which means it only has 2 total. The first shell only holds 2, though, so it's happy. The goal is to get a full outer shell. Usually that means 8, but if you're dealing with the first energy level, how many electrons does the first energy level hold? Just 2. And so helium is happy with its 2. Lithium, atomic number 3, has 2 in the first shell and 1 in the third to make 3. It's in column 1, so you can see it has 1 valence electron. What would lithium want to do to become happy? Yep, get rid of that 1. Now this whole energy level is gone, and now it technically only has 2 valence electrons because this is the valence shell now, but it's happy just like helium is. So helium and those that are nearby, like lithium and beryllium, are happy with just 2 valence electrons because they're only dealing with that first energy level and it only holds 2. But basically when you're deciding what will it do, when I asked what does lithium want to do and Michael answered me, you really want to think, well, there's 2 choices. I either have to steal enough to get to 8 or I have to lose everything I have in the outer shell. So what's easier, steal enough to get to 8 or lose everything I have? Well, it depends on how many. How many you would have to steal, how many you'd have to lose. So nitrogen is in column 15, it has 5. The 2 choices are to lose all 5 or to steal 3, because that would get you to 8. Which is easier, lose 5 or steal 3? Steal 3, because 3 is less than 5. So whichever one is a smaller number, that's the way it's going to go. But those atoms want to do one of those things. They either want to steal or gain. They either want to steal electrons or lose electrons to get that number that they want. Your metals are to the left of the duct tape. Are the elements, the metals to the left of the duct tape, typically stealing or losing? Column 1 has 1, 2 has 2. All the short columns technically have 2, but there's weird stuff going on. Aluminum, column 13 has 3. If you have 1, 2, or 3, like all the metals do you want to steal or lose? Lose. It's easier to lose 1 than it is to steal 7. It's easier to lose 2 than it is to steal 6. So all of your metals are losers. And just like my stupid joke, when you lose an electron, you become positive. Good. And there's a name for that thing that's now positive. It's called a cation. This is a new vocab term, and I want you to know it, so study it. Ion just means it has a charge now. Cation is more specific and tells you that it's a positive charge. So your metals lose electrons and become cations. Your nonmetals, like columns 15, 16, and 17, if you have 15 electrons, what are you going to do? You have 15, or I'm sorry, you don't have 15 electrons, I misspoke. If you're in column 15 and you have 5 electrons, what are you going to do?
Steal.
Steal how many? 3. Yep, so you're going to steal 3. If you're in column 16 and you have 6 valence electrons, what are you going to do?
Steal.
Steal 2. And if you're in column 17 and you have 7 valence electrons, what are you going to do? Steal 1. So that means all of your nonmetals are stealers. And when you steal, stealing is bad, it's negative. So your nonmetals tend to form negative ions. There's a vocab term for that too. Negative ions are called anions. So I want you to know those two terms. Cations are when you've lost and become positive. Anions are when you've stolen and become negative. Now there is a third option that we're going to talk about later in this chapter where they could share electrons with somebody, but we're not going to go there right now. Now the short columns I briefly mentioned, columns 3 through 12, they all technically have 2 valence electrons, but like scandium, Sc, the very first one in that block, has 2 valence electrons in energy level 4, and now it has more that it needs to put somewhere. It's actually backing up to a part of energy level 3 that it skipped and filling in part of energy level 3. So it's weird. It technically has 2 valence electrons because it started to fill up energy level 4, but now it's backtracking and filling up the rest of energy level 3. So it still technically has 2 valence electrons the whole time it's going
So you're saying
back.
it's got an empty third energy level,
Yeah,
but it's got valence electrons in 4?
yeah. It filled up 3s and 3p, but it has not filled up 3d yet. So it fills up, I'm only talking to Andrew right now, you guys ignore me. It has filled up 3s, and it has filled up 3p, and then it fills up 4s, and now it's backtracking to 3d, which can hold 10.
We're
So
only
there-
got like what?
So the whole time
You said
we're
two,
filling
it's like
in
at 2 and 3 times, you said?
scandium, since it's the first one in that block, would have 1 here. I just put a 10 here to show that it holds 10. So scandium would have a 1 here, titanium would have a 2 here, vanadium would have a 3 here. You get the idea.
Oh, okay, I get it.
And so as we go
think
from
we learned
scandium
that.
all the way over to zinc, we're filling this in, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But the whole time, we still technically have 2 valence electrons, because 4 is your valence shell, not 3.
Oh, okay.
All right,
Okay.
So that was just for Andrew. Now back to you guys.
I think we learned that or something. But I don't remember.
Probably did.
Chemistry.
All right, so the transition metals, they are metals. They technically all have 2 valence electrons, like I was saying. And so they want to lose electrons and become positive. But they're weird. Since they're kind of bouncing back and forth between 2 different levels, sometimes they'll shift their own electrons around to become slightly more stable. And so there are elements where sometimes they'll lose 2 and become a positive 2. And on another day, if they're with a different element, they might lose 3 and become a positive 3. You know, they're kind of wishy-washy like that. You can't say, oh, it's always going to be a positive 2, because it depends on which other element they're with. So the transition metals, you should know basically everything to the left of the duct tape, except for hydrogen, is a metal. And all those metals like to lose electrons and become positive. Your nonmetals to the right of the duct tape like to steal electrons and become negative. So if you're a metal and you're trying to give away your electron, who do you want to go find? to give it away to? A nonmetal, because the nonmetals want more. So metals and nonmetals are the perfect match. So far, every time we've been talking about this stuff, we've been talking about, oh, I just want to lose or I want to steal. And we haven't really talked about who you're losing to or stealing from. These atoms aren't just by themselves. They're with other atoms of different elements. And so this is all happening at once. Really, the metal loses whatever it wants to lose and gives it to a nonmetal who wanted to steal. So it's not really losing and stealing, it's really transferring. The metal transfers the electrons it doesn't want to a nonmetal. And we'll look later how you can have like different amounts of each to make everybody happy. So, I forgot that. So I think we're ready for our checkup now. Let me just talk about these and then I'll hand it out in a second. If you want to know how many total electrons something has, where would you look? Don't tell me the answer to this, because you're all going to have to do this on your own. But bromine, a totally different one. If I want to know how many total electrons bromine has, how would I do that? Not just the outer level, but all of the levels. How many total electrons does bromine have?
35.
Vadan? The atomic number. Bromine's atomic number right there in blue is 35. That means if you counted up all of the energy levels, it would have 35 electrons total. But we really only care about the outer shell, the valence electrons. So how many valence electrons would bromine have? What? I heard it. Sarah says 7, because it's in column 17. And for the teens, you subtract 10. So bromine has 35 total, but only 7 in the outer shell. If you have 7 in the outer shell, you would draw a dot diagram where you put Cl in the middle and put 7 dots around it. But can you just place the dots anywhere you want? No. Spread out to the 4 sides first. Top side, bottom side. And then, if you still have more, keep going and you'll have to start doubling up. If chlorine has 7 valence electrons, what does it want to do? Does it want to lose or steal? How many does it want to lose or steal? Or is it happy and it just wants to stay the way it is? What would chlorine do since it has 7 valence electrons? It would steal 1. You either have to steal enough to get to 8 or lose everything you have. It's a whole lot easier to steal 1 so that you have 8 than it is to lose 7, because 1 is less than 7. So it would steal 1. Stealing is bad, it's negative, right? So chlorine would have a -1 charge. And what's the name for something that has a negative charge? Cation, anion, or atom? Anion. The T in cation looks kind of like a plus sign, right? Cations are the positive ones. Anions are the negative ones. And what would the charge on an atom be? Neutral. Neutral or 0. Very good. All right. Now, if you want to keep a periodic table out, because you can't see this one very well, you can keep a periodic table out. But other than that, please kind of tuck things away. Don't tuck your notes away too far, because we're going to get them back out soon. Let's start from the other side. All right. I want you to treat this like a quiz. Fill in the table without the help of anybody else, without asking me questions, because I'm not going to answer them. Just do your best, write your name on it, and then flip it upside down when you're done. Okay, flip your papers back over, please. Please make sure your name is on it because you'll be passing it forward in just a minute. And you're going to grade your own right now when I put the answer key on the board. So mark it wrong if it's wrong. There's 6 boxes in each row, which makes 18. And in order to pass, you need to get 15 or more correct out of 18, which means you can only miss 3. If you miss 4 or more, it's okay. That just means you need a little extra help. And so at the end of the hour when we work on our homework, Andrew or I will pull you aside and work with you instead of letting you work on your own. So here we go. I'll have to do the dot diagrams over here because the board won't let me draw on it today. So strontium is atomic number 38, so it has 38 electrons total, so only 2 are in the outer shell. We know that because it's in column 2. So when you draw the dot diagram, you put SR for strontium, and then you put your 2 dots in 2 different places. Doesn't matter which 2 sides, they just have to be 2 different sides. Then strontium will lose those 2 and become a positive 2 cation. Phosphorus is atomic number 15, so it has 15 electrons. 15 minus 10 is 5. So here you're going to draw 5 dots. You have to spread out the 4 to 4 different sides first, and then just double up once. It doesn't matter which side has the double, but you should have 3 sides with just 1 and 1 side with the double. So that's what phosphorus would look like. Since it has 5 and it wants 8, it'll gain 3, or you could have said steal 3, and it will become a -3 anion. Neon's atomic number 10, so it has 10 total, but only 8 in the outer shell. We know that because it's in column 18, and 18 minus 10 is 8. So for neon, I'll do it here. Since it has 8 valence electrons, you'd spread out your 4, and then you'd go back and double up. 5, 6, 7, 8. So basically all 4 sides should have a pair of electrons. That means that it's happy and it wants to do nothing. For the charge, you could either say 0 or neutral, and we just call it an atom. It's not an ion if it doesn't have a charge. There you go. Any questions on those? So give me a score, either a minus however many, or a score that tells me how many you got correct. Give me a score on that, please. Make sure your name is on it and hand it forward. And then I'm gonna do like 5 more minutes of notes. So please get your notes back out. Oh, so close. So